Hi, I'm Sarabjeet Singh, a PhD student at the University of Utah, and today I'll be talking about our work Epic, which talks about efficient packing for CNN inference built upon a state-of-the-art work Cheetah. So modern day services are heavily dependent on deep learning, and over the past decade, these algorithms have been so successful with applications ranging from medical diagnosis to facial recognition to credit risk analysis that machine learning is now integral to services availed in everyday life. We're approaching a world where one such model, namely convolutional neural network, have demonstrated better than human accuracy over a variety of image classification tasks. However, these classes also come with limitations such as latency, 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 which raises a privacy concern. Typical machine learning as a service model solicitates access to raw user data, upon which model trains or infers, which leaves sensitive user data vulnerable to attacks. Fortunately, cryptographic techniques like homomorphic encryption or HE offers functionality of performing computation over encrypted data. However, these provable mathematical guarantees comes at a cost of massive overheads. For instance, one of the early HE-based evaluation of CNN reported inference latency of up to 5 orders of magnitude slower than inference over unencrypted data. In this work, we'll take a look over a more state-of-the-art HE-based CNN accelerator called Cheetah, which claimed around 200 millisecond inference latency using 580 millimeter square chip. We'll first go over the basics of homomorphic encryption. Once we understand the underlying kernels of what HE entails, we'll take a look at how Cheetah builds its setup of utilizing HE cryptographic technique to perform CNN inference. Next, we'll characterize Cheetah and identify its bottlenecks. Finally, addressing these bottlenecks, we present EPIC, an encoding technique that effectively improves the energy footprint by over 10x with respect to Cheetah. We conclude by quantizing this comparison in charts and listing down a set of key observations that we encountered during this work. All right, then, let's start by refreshing our basics of homomorphic encryption. Homomorphic encryption is this magical way of encrypting things, such that computations, when performed over encrypted data, results in an output which is the encryption of the same computation being done over the respective unencrypted data. What I mean by that is, let's say Alice has sensitive numbers x and y, and wants the results of the addition of x and y. Alice is given access to this remote adder, which takes in x and y and outputs out equal to x plus y. Now, given the sensitive nature of x and y, Alice does not want to reveal her raw data to the remote and potentially insecure adder. So homomorphic encryption encrypts x and y to ciphers, which are added together by the remote compute, returning a result which, when decrypted, is the same value as out. This encryption scheme is called additive HE scheme, where compute performed over addition without ever having access to the raw user data. Modern day HE schemes provide Boolean logic completeness, which was first introduced by Gentry in 2009, when their work proposed basing HE on the hardness of ideal lattices, more specifically, the learning with error problems. A sensitive data is first encoded as a polynomial of degree n with log cube bit width coefficients. This polynomial is encrypted using a variant of LW-based encryption scheme, resulting in a pair of polynomials. Security guarantees of LW comes from adding a small explicit noise during this encryption process. While performing computations over these noisy cipher, this noise increases. If left unchecked, this noise grows beyond the bound and affects the encoded data, hence resulting in incorrect result upon decryption. So typically, ciphers come with a depth that labels how many complex operations you can perform without going beyond this bound. Theref- Therefore, Ideally, we want a high depth, but that increases our cipher bit width. With increased bit width, the polynomial degree increases as well. This is demonstrated in this figure from Microsoft Bootcamp, which captures the source of massive compute requirements of HE. The key takeaway from the slide is that in order to maintain a reasonable functionality and security, we need large complex polynomials as a basic data type. For instance, recent work F1 uses a parameter set of n equal to 16k degree and q as 512-bit widths, which makes a polynomial as large as 1 megabytes. Now, let's take a look at the basic operations we can perform on these ciphers. Modern HE schemes are functionally complete, which means that both additions and multiplications are allowed. Consider two input cipher polynomials. Addition is just coefficient-wise addition. Know that all these operations are modular, so that means that each cipher is constant. Scalar multiplication can be visualized as a scalar value multiplied by each coefficient individually. Polynomial multiplication is a little bit more non-trivial, since it is performed by multiplying each coefficient with every other coefficient, which is order of n square multiplication. To, re to reduce the polynomial multiplication complexity, the convention is to convert the polynomial from coefficient domain to evaluation domain, evaluated at nth root of unity. This reduces polymult to simply coefficient-wise multiplication, which is order of n. This domain conversion is achieved by number theoretic transform on entity, a special form of discrete Fourier transform, and requires order of n log n steps. So typically, polynomials are kept in evaluation domain to avoid this conversion cost. As mentioned earlier, HE parameters can be very large and can vary across applications. Implementing large and flexible bit width logic is expensive. Convention wisdom is to use residue number system or RNS, which takes an input polynomial of degree n and q bit coefficients and decomposes it to multiple smaller bit width and same degree polynomials. These residue polynomials have the independent functionality, which means that computation can be performed on them individually and possibly parallelly. And finally, the result can be combined to output polynomial. So far, we talked about ciphers that encrypts a single value with a polynomial. In 2011, Gentry demonstrated that multiple slots within the polynomial can be utilized to encode a vector of data, reducing the cipher overhead by up to n times. However, this limits the completeness functionality of homomorphic encryption, since individual values from a polynomial cannot be extracted and used as inputs. So an operation called automorphism is used to rotate or permute these slots within a polynomial. This step can only be performed on the coefficient domain and hence requires subroutines with domain conversion using extensive entity. Additionally, a cipher rotation results in a cipher which is not decryptable by the same encryption key. In fact, it can be visualized as the same raw data encrypted with a similar automorphism. In order to restore the modification in key of the rotated cipher, a key switching operation is required. Key switching operation is also expensive since it requires hints as input. With n possible rotations, n hints are required, resulting in large data movement. Therefore, as we try to pack more data, there exists a trade-off between the complexity and the cipher reuse. We consider the state-of-the-art work on homomorphic encryption-based CNN inference, TIDA, as our baseline. TIDA uses the following pipeline. Input feature maps from a layer are first encoded as polynomials. These polynomials are encrypted and sent to a cloud for convolution. Cloud multiplies the activation cipher with kernel polynomials, resulting in an output neuron cipher. Since homomorphic encryption can only perform non-linear layers trivially, the output neurons are transferred back to the client, which performs those non-linear layers after decryption and prepares them for the next layer. Since the convolution model never leaves the cloud, the kernel polynomials need not be encrypted. Well, this works pretty well for a single data. Ideally, we want to reduce data footprint by first encoding multiple data. So Cheetah follows the following pipeline. Uh, First, for input feature maps, pack as many values from a single activation and single channel XY. If there are leftover slots, go across multiple input channels, CT. Therefore, a single input cipher captures XT, XYT, CT values. While encoding weights, Cheetah packs exactly one value, which is replicated across these slots. If there are multiple input channels present in activation polynomial, Cheetah pads the slots with zeros, since only like channels should be multiplied. Upon multiplication, a partial sum cipher is generated. To reuse the activation cipher, they fetch the next weight and perform the same multiplication operation. But in order to accumulate partial sums must be rotated after each polymer so that the respective partial sums can be aligned before addition. Therefore, after each activation and weight multiplication, there is an expensive cipher rotation operation that requires automorphism, entity, and key switching. Overall, Cheetah packs multiple activations in cipher polynomial for efficiency. It feeds single-valued weight polynomials to be multiplied with these activations, generating partial sums that must be rotated before accumulation. However, we believe that the encoding uh, that just however we believe that encoding just a single value in weight polynomial is inefficient and results in large data movement. For instance, given a RSCK dimension weight, in order to reuse the activation cipher, RSCK polynomials must be fetched. Considering a polynomial as a underlying data type, the reuse distance of weights is too large to be able to cached on chip on realistic on chip, resulting in every weight to be memory bound. While the latency of this memory access can be hidden behind partial sum rotation, the accesses amount to large off-chip energy. Additionally, for many layers with CT greater than 1, the weight polynomials are padded with zeros, resulting in ineffectual computations. Such computations waste resources, resulting in inefficient implementation. Overall, we identify memory fetches and ineffectual computations as two major bottlenecks in Cheetah. In this work, we address these two issues by proposing Epic, an efficient packing for inference using Cheetah. And the basic idea is very simple. Pack multiple values in the weight polynomial. So we start by packing input features in a similar fashion as what Cheetah did, where X, Y, T, CT values are captured by a single input cipher. Now, in order to multiply activations with like channels, we first pack all weights of CT channels from a single kernel. Usually, the face size of input features XY is much larger than the face size of a kernel, which is RS. Therefore, to fill the remaining slots in the weight polynomial, multiple kernels must be packed. So overall, RS, CT, KT values of weights are packed within a weight polynomial. This means that first, weight polynomials footprint reduced by RSCT-KT times, which is approximately equal to the degree of polynomials, which directly translates to n times lower memory accesses. In fact, with n times less polynomials, in most cases, weight polynomials can now fit in on-chip caches. Secondly, Cheetah encoded useful information only in one part out of CT parts of the weight polynomial. Rest were padded with zeros. Epic tries to make the best of polymer by utilizing all these slots. However, however, Epic does comes with a disadvantage. Since multiple weight values are packed within the polynomial, It too must be rotated after each multiplication, requiring costly entities and key switching. Epic makes the case that this is a justified trade-off, as the benefits obtained by lower memory accesses and reduced ineffectual computations outweigh the overheads of additional rotation. So we compare Cheetah and Epic by running encrypted inference on ResNet 50. Similar to Cheetah, we present results only for server-side convolution operations. Since most CNNs perform a nonlinear layer after every convolution layer, the HE parameters can be reduced to serve a depth of just one cipher-to-cipher multiplication. We use a popular scheme BFV to extract parameters, which are n equal to 1024 degree, and log q is equal to 19 bits. Polynomials are decomposed into four residue polynomials. We evaluate these designs on a generic CNN architecture, augmented with a modular arithmetic logic. The chip consists of 16 PEs connected using a TOS network and equipped with the L2 class to store activations, weights, and key switching heads. Each PE is equipped with smaller registers that feed the inputs to the modular MAC and store the partial sums. So let's take a look at the comparison results now. The left figure presents energy breakdown of performing inference on Cheetah and Epic. Right side figure presents subroutine level breakdown for performance. There are a couple of interesting observations that I want to point out to you. First, if you look at the blue bar on the left, most of Cheetah's energy consumption arises from off-chip accesses. As mentioned earlier, this is due to large number of single-valued weight polynomials in the packing scheme. Epic sharply reduces that data movement by first providing an efficient packing scheme that reduces weight of off-chip accesses by n times, and then caching that smaller number of polynomials to capture reuse. Overall, Epic has 10 times lower energy footprint than Cheetah. Secondly, if we look at the performance numbers on the right, we know that entity is the major contributor to the delay. This is because after each poly multiplication, which is order of n and can be implemented in a single cycle by providing parallel max, we must rotate partial sums, which is an order of n log n operation. While the multiplication, while the order n multiplication can be performed in parallel with n max, entity requires order of log n extra delay. Even though Cheetah requires many off-chip accesses, the latency can actually be hidden behind the entity latency. Third, by reducing the number of ineffectual computation, we reduce the total number of activation cipher and weight polymers, essentially lowering the overall inference latency by 2.2 times. Lastly, we note that in some layers, we end up performing worse than Cheetah. As mentioned before, Epic requires 2x rotation over Cheetah since it rotates both weights and partial sums. Hence, in cases where Cheetah does not pad with zeros, Epic ends up taking more time. However, this happens for only a handful of layers, and given the reduced memory accesses and energy, and hence energy, this is a reasonable performance penalty. Finally, we would like to conclude by listing down a set of key observations. First, while the upcoming works talk about how fully homomorphic encryption schemes are heavily memory bound due to expensive operations like bootstrapping, we would like to take a step back and demonstrate that even current state of the art still haven't fixed this bottleneck in level schemes. Secondly, we would like to drive the point that packing strategies can play a crucial role in operation count and data footprint. Based on these observations, we propose a weight packing strategy, EPIC, that results in 10x lower energy with 2.2x speed up over the state-of-the-art inference work. That concludes my presentation, and I'll be happy to take any questions or concerns now.
Okay, thank you very much. Yeah, I will let me allow you to talk. Let me just yeah, enable talking to you, Sarabjeet, so you can answer to questions. Okay. Let's check the chat. I see a question there. It says, aren't the weights plain text in the server side? Why is it expensive to rotate them?
Hi, can you hear me?
Yes.
Yeah. Uh, right. As I mentioned earlier, yes, the weights are in plain text at the server because they don't have to move outside the server. But as I mentioned earlier, to reduce the complexity of polynomial multiplication, these polynomials are usually converted into evaluation domain, and rotation can only be performed on coefficient domain. Right. So to perform that rotation, we have to do that conversion from evaluation domain to coefficient domain, which requires us to perform an entity operation. And that is what's expensive over there.
Okay, thank you very much.
Sarabjeet, this is Ross speaking. Gusto, do
Yeah,
we have time for
sure.
one more question? Thanks.
We have time, actually. Have a few more. Yeah, I mean, we have a few more
Thanks.
minutes. Yeah.
So Sarabjeet, this is very interesting actually. We had a very similar idea actually, and but we haven't implemented it. So this is the proof that actually this thing might work. Is this work? Did you publish this work already?
Not yet. I mean, this apart from this workshop, not yet.
Because this is kind of interesting. This is interesting whether the weights are actually in the plain text domain, or even if they are encrypted, because the weights might not necessarily be in interesting. But it's interesting the gain in energy efficiency that you have demonstrated. Okay, so I look forward. I mean, to the publication of this work. Shouldn't be a problem to publish it. It's a clear improvement, right? Thanks.
Thanks, and maybe we can talk more about it offline as well.
Please, yes.
Any other questions? I have one actually, Sarabjeet, maybe a clarification one. At some point in your presentation, you mentioned like the processor architecture that you use to evaluate EPIC, right? Is that architecture something that you have also developed as part of this project, or is that something that you are taking from somebody else, let's say?
So yeah, the architecture that we presented is we haven't taken that from somewhere. It's a generic architecture that we designed, and the purpose to make it very generic was that the optimization that we propose in Epic is a software and algorithmic optimization about packing more things, and it's very independent of the underlying hardware. So we wanted to drive this point that before even looking to hardware, there are algorithmic optimizations which are very specific to homomorphic encryption that we can exploit to reduce the data footprint and even computational intensity of these applications.
Thank you. Thanks. Okay. Any other question? We still have a couple of more minutes. Okay.
Augusto, yeah, I do have another question. Sorry.
Oh, sure, please. Yeah.
So, Sarabjeet, a question for you. The evaluation results, right? When you look at EPIC versus Cheetah, right? Do you so what do you do in between the layers? Do you decrypt and re-encrypt, or so how is the overall kind of inference time and energy being evaluated?
Right. So we assume the cheetah model where the server does not perform nonlinear layers. So that means after every convolution layer, the output neurons that you generated are generally sent back to the client, who actually decrypts it and performs nonlinear layers and encrypt it again to send back to the server. So, so yes, the noise is actually reset after every layer since it's being decrypted. Hence, we don't have to do bootstrapping here.
Right.
And the results that we present here are similar to Cheetah. We just present the server-side latency.
Yeah. Okay, excellent. Yeah, I was thinking that that was the case. But you know, this optimization that you're talking about, we evaluated it in the context of also the weights encrypted, right? And even relatively large neural network, you end up with the working set size that basically remains small and constant in between layers, which is kind of very interesting.
If I may, we also calculated. I did not present the communication latency, but we also calculated communication latency within this inference, and it turns out to be assuming that the communication of 1 bit the speed is 1 gigabits per second. The whole network requires around 200 to 400 millisecond of communication latency. I believe that some kind of hybrid design where some layers are performed on server on an encrypted domain, while other layers are performed by the client themselves would be much more efficient.
Yeah. So the only issue that you have when you do that, it's not so much about the performance, but it's about the fact that the client is actually computing a part of the neural network, right? So the data life cycle basically changes completely because there's a lot of interaction with the clients that otherwise in the clear text would never occur. But it's a model, right? That you say that it's client aided. Okay, thanks.
Okay, thank you, Rowan. Thank you, Sarabjeet. Yeah. So thank you very much. Yeah, we will move to our next talk.